Let's go ahead and get started then. The topic we're going to be talking about today, transportation, transshipment, and assignment problems. So we're going to first talk about the transportation example. These are just variants of linear programming, linear integer, binary integer programming. Bless you. Okay. Okay. So, in the previous modules, we saw how integer programming is useful in making decisions. So basically, helps us specify how many of a product we're going to buy, sell, do whatever it may be. Like our golf cart going around. So, in this module, we're going to expand upon this principle. We're going to discuss three types of problems. Like I said, this is transportation, transshipment, and assignment problems. We'll see how we can extend the ideas of linear and integer programming to address these problems, okay? So these are part of a larger class of linear programming problems known as network flow models, which we're going to be covering in the next module. And they possess special mathematical features that enable development of very efficient, unique solution methods. And methods are variations of traditional simplex procedures. Outside the scope of the class, the point is that these have special characteristics that allow you to solve for very, very large instances of these types of problems. Okay? So, okay. So, essentially, a product is transported from a number of sources to a number of destinations at the minimum possible cost. Each source is able to supply a fixed number of units of the product, and each destination has a fixed demand for the product. So the linear programming model has constraints for supply at each source and demand at each destination. All constraints are equalities or equations in what we refer to as a balanced transportation model, where supply equals demand. And constraints that contain inequalities are in unbalanced models, where supply does not equal demand, which is usually the case. Okay? Okay, so that's the definition, but it's easier if I actually do a problem. So here's the problem. How many tons of wheat to transport from each grain elevator to each mill on a monthly basis in order to minimize the total cost of transportation? So here's what we have. We have these three grain elevators out in Kansas City, Omaha, and Des Moines. Okay? The supply at Kansas City is 150 tons, Omaha is 175 tons, Des Moines is 275 tons. So we have a total supply of 600 tons. Now we have these mills, which basically mill process the grain itself. Those are located at Chicago, St. Louis, and Cincinnati. The demand, Chicago is 200, St. Louis 100, Cincinnati is 300. So we have a total, essentially, demand of these three mills of 600. Okay. Now, this matrix down here at the bottom basically tells us the cost. If we send our grain from Kansas City to Chicago, it costs $6 a ton. Kansas City to St. Louis, $8. Kansas City to Cincinnati, $10, and so on and so forth. So essentially, here's the question we're asking. How much should we send from each grain elevator to each mill? Okay? So we have 150 tons at Kansas City. Where should we send it? Should we send it to all of it to Chicago, all of it to St. Louis, all of it to Cincinnati, or do kind of some mix and matching? Okay? So how do we go about formulating this? Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 decision variables here. Okay? The 9 decision variables basically say we have a decision variable we're going to call X1A, which is how much do we send from Kansas City to Chicago. X1B, how much do we send from Kansas City to St. Louis? Okay? So we want to minimize that total cost. All right? Here's the objective function. So if we have this set up in Excel, any ideas what statement we would use to make this super simple to create an objective function? Sum product. Okay? Anytime you see a lot of decision variables and a constraint, a lot of times you can almost bet there's going to be a sum product involved. So what we would do is we would simply just set up another matrix in Excel. I'll go over how to do this here in just a moment. And we would take the sum product of that matrix with this cost matrix. Okay? And it would give us this. It would give us this objective function. subject to these 6 constraints. X1A, X1B, X1C, add those up, is equal to 150. Simply saying the amount of grain leaving Kansas City going to Chicago, St. Louis, and Cincinnati, that total amount must be equal to 150. This is how much you have, you're shipping it out, it has to be equal to 150. Amount leaving Omaha has to be 175, the amount leaving Des Moines has to be 275. The last 3 constraints says the amount coming into Chicago has to be 200, the amount coming into St. Louis has to be 100, and the amount coming into Cincinnati has to be 300. All right? That's all there is to it. And then Xij is greater than or equal to 0, meaning that you can't send a negative amount. Simple as that. So this is essentially the model. Okay? It's a linear programming model. All right? Here's kind of what it looks like, the network itself. So let's go in and see what this would look like when we actually solve this. Okay. So, what I did here, let me do it here. I had it done 2 different ways, just to kind of prove a point. You can see how I entered this in. I actually hard-coded it. So that would take a little while for me to hard-code it. Okay? So what I did on another one, and these are posted on the web, is I went in and showed you that you can just simply use a sum product. So C5E7, those are your decision variables, those in the blue. Your cost matrix down here in the red, your sum product of 2. That quick, you've got your objective function. It could be a huge matrix, 100 by 100 matrix in theory. Okay? Do a sum product. It wouldn't take any longer to formulate a 100 by 100 matrix, 100 by 100, which would be 10,000 decision variables, than it would a 3 by 3. The only additional time it would take is just either dragging or, it's like, well, let me go and look and see what this corner is. But in terms of typing the 2 in, take the exact same amount of time. Okay? Our supply, this is just a supply. Here's just the demand, just the numbers I put in. So when I looked at the actual grain shipped, it's just the sum of these 3 columns, C, D, and E. Okay? So right now I'm not shipping anything, so that's why it's 0. If I were to put something in like 10, we see how this guy's going to jump up to 10. Okay? Change it back to 0, goes back to 0. Okay, so let's go up here to data, click on solver. All right, so what do I have? Okay, what I have is changing, or I want to set my objective function C10, minimize this by changing C5 to E7, these decision variables, subject to these constraints. Essentially what I'm saying is C9 to E9, how much I'm actually shipping has to be equal to C8, E8, the demand. All right? G5, G7, how much I'm shipping must be equal to the supply. Make the constraints non-negative. That takes care of everything has to be greater than or equal to 0. Simplex method, because it's a linear problem. Boom. There's the answer. Okay. I take 25 from Kansas City to Chicago, 125 from Kansas City to Cincinnati, gives me a supply of 150. Omaha to Chicago, 0 to St. Louis, 0. Send everything from Omaha to Cincinnati. From Des Moines, I split it up. 175 goes to Chicago, 100 goes to St. Louis. And my minimum cost would be 45.25. Right? Simple. Okay. I'll just show you how to set it up. Okay, so sometimes we have an unbalanced problem in which supply exceeds demand or demand exceeds supply. So in real world problems, this is usually the case. The 2 aren't usually perfectly balanced, okay? Now models can become much more complicated when you start going in looking at the economics of having an unbalanced supply and demand. Because what happens is, in reality, the cost structure is dynamic in the real world, okay? So let's suppose I'm selling bananas, okay? I remember one time when I was a kid, Yeah, I don't know what had happened. I just know that when I was a kid, on Friday evenings, we'd come to the bank down in Bluefield, West Virginia, or Bluefield, Virginia, Dad would get his checks cashed after working all week, and we'd go out and get something to eat. And we would go down the avenue, and there was this, some of you guys, I don't know if you remember it or not, if you're old enough, but the State Line Market was right there on the West Virginia line, going down the avenue, and I don't know, they had bananas, like 3 pounds for $1. So it's like, well, let's get us $10 worth of bananas. You know, he's like, yeah, we need 30 pounds of bananas, you know. Finally, I remember it got up to 10 pounds for $1. I still remember that. It's like, yeah, we're going to load up on bananas. You know, it's like, yeah, what are we going to do with all those bananas? So there was an oversupply. And so when there's too much supply, what happens to the cost? Cost goes down. When there's not enough supply, what happens to the cost? The cost goes up. You know, these are markets. So that becomes very complicated. We're not going to take that into account in these problems. But the price itself sometimes becomes dynamic. Not sometimes, it's always dynamic. If there's too much of something, the price goes down, you're trying to get rid of it. If there's not enough, it's like, I'm not selling my bananas. You know, it's like, you want them, you're going to pay for them, that sort of thing. Okay? So these problems can become much more complicated. So, like I said, real-world problems, this is usually the case. When this happens, we must include inequality constraints instead of equality constraints or equations, or we'll get an infeasible solution. The reason why you get an infeasible solution is because it's an infeasible problem. If supply doesn't equal demand, you can't make supply equal to demand. Okay, it's simple as that. Okay, so for example, suppose that the demand at Cincinnati increased from 300 tons to 350 tons. Now the total demand, 650 tons, is greater than the total supply of 600 tons. How would we allocate resources now? Okay? Well, everything's going to be exactly the same for the most part, except these bottom 3 constraints. What this tells us is essentially, what's it say? That the demand at Cincinnati increased from 300 to 350 tons. So we have more demand than we have supply. So this means when you look down here, X1A, X2A, X3A, the amount going to the grain elevator, okay, is going to be less than its demand, okay, because less than or equal. It may be as much as the demand, okay, but you don't have enough supply to equal the demand. So we have a total demand of 650, we have a total supply of 600, so somewhere we have to make up 50 tons, okay? So the way we do that is we simply just use an inequality. It says, well, allocate what you can, but we don't have enough. So somewhere, either all 3 of these grain elevators are going to be lacking, deficient, or one, or some combination, 1 or 2, whatever it may be. Okay? So let's take a look at the problem. Right, everything's exactly the same, except notice here now we have an inequality instead of an equation. Hit solve, and we get 4225. What did we get a moment ago? 4225. Now, what happened? Okay. Well, what happened in this particular case, see how these numbers, this 25, 0, 125, everything went to 150. Here it was 0, 0, 175. That's 25, 150. But what's our total cost? Our total cost is the same. Just allocated them in a different way. Okay? There's probably multiple optimal solutions to this now that I think about it. Why is this the case? Well, the reason why it's the case is really nothing changed in the problem. We just said that we have more demand, but we still have to allocate these from our supply. Okay, we still have to allocate it. So in this particular case, the constraint really just kind of gave us more flexibility. Okay, this inequality constraint gave us more flexibility, more feasible solution space. This is something that we haven't covered in this class, and we won't. I just showed you guys how to formulate it. But remember earlier in the class when we talked about the polytopes, maybe our polytopes look like this, okay, that sort of thing. And we said that all of this is a feasible solution. Right? Now, what happens is that's when we have an inequality. When we have an equation, all of a sudden what happens is our feasible solution space gets bounded to our perimeter. Because when you say it has to equal a certain value, okay, it gets stuck to that perimeter. Now that can create problems sometimes. And the reason why it can create problems is because you get infeasible solutions. You don't really have a region, you only have a line. And if all of these constraints don't intersect at the same point, then it becomes infeasible. Okay? So you have to make sure that if you have these hard constraints, these equality constraints, that the problem is doable. Because very, very quickly when you start putting in equalities, what happens is you may have something that looks like this. You have these two intersect, okay? Well, if you have this region down here, you know, that you're using, and you have another, say, constraint that comes through like this, okay? Well, this region is a feasible solution. But if you have these two as hard constraints, then this guy right here would have to intersect at that. 3 lines would have to intersect at one point. 4 lines, 5 lines, whatever it may be. Okay, so you always have to be aware of that. And solving this type of problem is a little more complicated actually when you do it by hand, but we're not worried about it because the computer takes care of it for us. Okay? Now let's turn the problem around. So now, what happens if supply exceeds demand? Okay? In this case, we'll not be able to ship all the product we produce. So now we have too much product. Before we had too much demand. Okay, now we have too much product. Therefore, we cannot constrain the supply to equal the capacity of each plant. So for example, suppose that the demand at Cincinnati is decreased from 300 tons to 200 tons. Now the total demand, which is 500 tons, is less than the total supply. Okay, so there was a fire or something that happened at one of these grain elevators. This happened a few years ago with an oil refinery, caused the price to go up. Okay, you had an oil refinery, you know, and when you look at how much oil, crude oil, we were able to refine, we're almost up against it. Okay, and the reason why we're almost up against it is because the market's efficient, it's smart. It figured out 30 years ago that about the maximum amount we're going to be able to extract out of the earth is X, so we're not going to build much more than X refining capacity. Okay, so if you had a problem with refineries, I mean, it could cause a huge spike in prices. In fact, a few years ago, I was teaching a system dynamics course, which is another type of modeling methodology, and I probably shouldn't have done it. And actually, I had a colleague come up and say, "You probably shouldn't do that again in class." But I did. So if you see my face, America's Most Wanted, you'll know what happened. What we were doing is, you know, I was working on projects for the Department of Homeland Security, doing research in energy, oil production, that sort of thing. And they got to doing a little bit of research on the amount of, on the refining capacity in the United States, okay? Actually the world refining capacity, but we specifically looked at the United States. And, you know, got to where I was working with the Department of Homeland Security and terrorists, that sort of thing, trying to model that. I got to thinking, like, you know, if you really wanted to, say as a terrorist, to really cripple an economy, I mean, how would you do that? Well, you know, knock down a few towers, okay, that was a disruption, kill a few people. I mean, I'm not trivializing it, but I'm saying that's ultimately what happened. But we recovered from that. You know, you had a couple of towers that was knocked down, that sort of thing, planes crashed. But if you had a coordinated attack, say, on the refineries in the United States, okay, that's something you don't fix overnight. You don't just blow up a refinery, and they go up pretty easy, to be honest with you. You don't just like, okay, it's going to be offline for about 3 weeks on this one. You're looking years to build refineries and repair them and that sort of thing. The problem that I posed is how many, if you wanted to use operations research to actually do it the right way, how would you do it? And you would be surprised. I mean, it was only something like 20 refineries you would have to take out to just basically, I think it was something like with just 20 refineries, you would reduce the refining capacity by 50%, which the models predicted at that point you would get about $20 a gallon for gas is what it would spike up to. Okay, and that didn't even take into account, the panic that would ensue. People, I don't have access to gas, and it would essentially, just cripple the economy. Really, really cripple it, because all of a sudden you don't just run down to Walmart and get a peach, because that peach, is shipped in from a truck, from California or Florida, wherever it may be. You don't just fly across the country, because now the cost of gasoline or kerosene is basically what they burn in jets have gone up and that sort of thing. And we went in and we actually modeled that and looked at strategically, which refineries that you would actually take out. It was all out in the open. I wasn't trying to hide anything. And I'm sure that the government's already investigated that sort of thing. But it was really, for me, it really kind of brought home, like, man, this is really something you don't think about. You think about having to essentially take out, what would it take to cripple our economy? We have a huge country, a huge redundancy in infrastructure and that sort of thing. And once that global supply, was taken down, then all of a sudden now, if you're another country, you're not going to just sell us, your refined fuel, because you're going to need it for yourself. So it's a very interesting study, really eye-opening for me and a lot of students in that particular class. Anyway, I don't know how I got off on that. Oh, supply and demand sort of thing. So in this particular case, the total demand is less than the total supply. Okay, so how do we allocate resources now? Well, basically do the exact same thing. Except we just go in and switch our constraints, solve it. So now the answer was what, 45, 25. Now it's gone down to 40 or 34.25. Okay. The reason for this is simply now you're just not shipping as much. You were shipping 600, now you've gone down to 500. But this is still done in an optimal way. Okay. And that's just how you formulate it. Okay. Now, sometimes one or more routes in the transportation model may be prohibited for whatever reason. Okay. I don't know, you're manufacturing something that's explosive, so you can't take a direct route from one to the next, so you gotta go through a tunnel or something like that. Okay, that is, units cannot be transported from a particular source to a particular destination. Because of this, because this is not a binary programming problem, we cannot just set the decision to transport from one city to another equal to 0. A lot of times in these types of models, we have to be clever. I've always used this word. We have to trick the model into making the correct decision for us. And a lot of times with binary decision variables models, I actually see the models as you're almost tricking the mathematics to give you something that the mathematics shouldn't be giving you. That's kind of how I've always felt about these problems. That the mathematics behind this is just going right along, it's just solving, and you're doing something like, well, we want it to be between 0 and 1, and a 1's going to mean do it, and 0 is going to be not do it, and that sort of thing. So we're always trying to trick these models to help us get the answers that we want. So we use a technique that's referred to the big Egmt technique. Okay, and the way the big Egmt technique works is to assign a very large cost to the path we want to be prohibited. Okay? And you see big Egmt techniques all the time in OR. Okay? By doing this, when the model is solved, it avoids assigning a value to the prohibited path. So how large should big Egmt be? Well, as a general rule of thumb, if big Egmt is 100 times greater than the largest value of the objective function, the model should work. Okay? So, for example, let's suppose we cannot allow products to be shipped from Kansas City to Cincinnati. What would the model look like now? Well, we need to make the value of the shipping cost from Kansas City to Cincinnati a large value. I'm going to say M is equal to 1,200. Okay? So this M up here, you see that? We put a big M in front of, that's the coefficient in front of x1c. We don't change anything else. We just put a big M in front of it. Big M just represents, it's a big number. So I take the largest value in the model, which was 12, multiply it times 100. I mean, it could have been 50. I could multiply it times 200 or whatever. It's just a couple orders of magnitude larger than any of the other coefficients. 6, 8, 7, 11, 1. 1. That should be 11. Four, 5, 12. Okay? Leave everything the same. Go in and solve it. Okay? So I'm going to go here, big M in. This guy's 1,200. Solve it. Everything's the same. So you'll notice that what happened here is that it zeroed this guy out. On the very first problem, this was 125. Now, this guy has been zeroed out, not because we forced it to be equal to 0, but because the model itself avoided putting a coefficient of 1,200 in, because it would make the objective function so large. Okay? And our value went up from 4525 up to 5025, because we took that route out. Okay, so like I said, there's problems in OR. You see this done all the time. It's just an easy way to make the model avoid plugging an answer in. And sometimes, in this particular case, we could have just forced that value to be equal to 0 and gotten around it. But in some models, you can't actually do that. You actually have to go in and trick the model. Okay? And that's it. Any questions with the transportation? Problems? Okay, well, let's go in then and take a look at transshipment models. Fairly short module. Transshipment is essentially an extension of a transportation model. Okay? Extensions of the transportation model. Well, what is a transshipment model? A transshipment model is a transportation model with intermediate modes. So instead of going from point A to B, we have to go from point A to point C through point B. Or we can still go maybe from A to B, but it may be more beneficial to go through point C first. Okay? So intermediate transshipment points are added between sources and destinations. Items may be transported from sources through transshipment points to destinations, from one source to another, one transshipment point to another, one destination to another, directly from sources to destinations, or some combination of these. Okay? So, the extension of the transportation model in which intermediate transshipment points are added between sources and destinations. This particular case, we're going to say, well, we got to, before we were just looking at the grain elevator, now we're going from the grain elevator. Before we even get there, we have a farm. And the farms are located in Nebraska or Colorado. So we go from Nebraska or Colorado to the grain elevator, then on to the mill itself. Okay? So here's kind of a pictorial of that. Before we were just looking at going from these grain elevators to the mills. Now we have to get from the farm to the grain elevator. So you may look at it and say, well, what's going to change about it? Well, the problem before is if we were in Omaha we could go straight, say, to St. Louis, okay? Well, now we have to get to Omaha first. So the amount we have going to St. Louis, if that's coming through Omaha, we first have to get that amount from the farms, okay? So it adds another layer of complexity to the problem. It's not bad, though. Essentially, let's go in and look at problem. Do I have the cost there? Yeah. Okay. Let's go in and look at this formulation. Everything is similar except these last three constraints, and let's see what they actually do. What we're saying here is we have x13 plus x23 minus x36 minus x37 minus x38. We can rewrite this to say x13 plus x23 is equal to x36 plus x37 plus x38, right? Essentially what this means is this. Is if we're going from 3, you can go from 3 to 6, 3 to 7, 3 to 8. The amount leaving 3 has to be equal to the amount coming into 3, right? So 1 to 3 plus 2 to 3 has to be equal to the amount leaving 3 to 6, 3 to 7, 3 to 8. Does that make sense? These last three constraints? Okay, so let's go in and look at this model. So what I have when I look at my total cost, notice that I have two sum products here. The reason why I have two sum products is because I have these decision variables, which is going from the farms to the grain elevators, the sum product of this matrix with this matrix, plus these decision variables, the sum product of this matrix with the sum product of this matrix. Okay? And then you can see here that I show how much is shipped from each farm to each grain elevator, then from each grain elevator to each meal. Okay, so now I have 9 plus 6, I have 15 decision variables. The way I do that is I put a comma between them. So I can grab one matrix, pull it down, put a comma, then grab another matrix. Okay? So it's a quick way of putting a whole lot of decision variables. Minimize C24, my total cost, and then just set these constraints, basically my supply and demand constraints. Solve it. And it says my total cost is now $12,400. Okay. Okay. So pretty simple. It's just an extension of transportation model. And then finally, assignment problems. These are kind of interesting. At least I think they are. Okay, the assignment problem, believe it or not, it's a special case of the transportation model. Okay, special form of linear programming model similar to the transportation model. What we do is we essentially force the supply at each source and demand at each destination to 1. Okay, so we trick it once again. Instead of saying it's like 150, we say, well, it has to be 1. Okay, and that forces it either all of it goes or none of it goes, that sort of thing. So in a balanced model, supply equals demand, and an unbalanced model, supply does not equal demand. Okay. So here's the problem we're working on. Now, this type of model is actually used in creating schedules. So if you look at, say the NCAA, there's 117 teams, different conferences. Who plays what, and when do they play? That sort of thing. That's pretty complicated. If you sit down and start trying to figure it out, it's like, all right, Well, we played you at your place last year. You're going to play us this year. So we have to play all of our teams in our conference. Okay, but then we have these other schools we're going to play. Why do we play them? Where are we going to play them? That sort of thing. This is put into a big model, okay? And it figures out, based on some criteria, who plays what when. Of course, you always have your end of season game where you play your rival in the state or whatever it may be. Okay? So here's the problem. We want to assign 4 teams of officials to 4 games in a way that will minimize the total distance traveled by the officials. Supply is always 1 team of officials. Demand is for only 1 team of officials at each game. Okay? So we have 4 teams, A, B, C, and D. They need to be assigned to, I guess this would be NC State, Georgia Tech, Duke, and Clemson. Okay? So the teams of officials, if they go to Raleigh, it's 210 miles. To Atlanta, it's 90. To Durham, 180. To Clemson, it's 160. Okay? So simple question. What teams officiate where? All right? So it's all the same nights. You can't have 1 team of officials officiating at 2 different schools. And, okay, so what do we do? Well, here's what I'm going to do. I'm going to have 8 constraints. Well, I'm going to have this objective function up here at the top, which is just simply a sum product of the distances times the decision variables. Do you go, say, from XAR, which is Team A going to Raleigh, AA is Team A going to Atlanta, AD is Team A going to Durham, AC is Team A going to Clemson. All right? They'll have to be equal to 1. Why is that? Well, let's take a look at the model here. So what we see is that I just put a 1 here. This is what the demand is. And then we just add up each one of these rows, or we add up each one of these columns, like this. Okay? Bless you. So I want to set my objective function, which is my total mileage here. It's just a sum product, okay, by changing these cells subject to these constraints. I plugged in this binary constraint. I don't think I need that binary constraint, actually. Let me see. Pretty sure I don't, because summing it to 1 is going to ensure that only one of these is going to have 1. But let's see. Let's hit solve and see what happens. Yep, I was right. Okay. So A goes to Atlanta. A goes to Atlanta. B goes to Raleigh. C goes to Durham. And D goes to Clemson. These sums are equal to 1. These sums are equal to 1. Minimum mileage is 450. All right. Assignment problem. Okay. Well, this is how a lot of assignment problems are actually done. Software that actually goes in and does it for you. Okay, one more problem. The job shop company has purchased 3 new machines of different types. There are 4 locations in the shop where a machine could be installed. Some of these locations are more desirable than others for particular machines because of their proximity to work centers that will have a heavy workflow to and from these machines. The objective is to assign the new machines to the available locations to minimize the total cost of material handling. Okay? Here's what we have. We have 3 machines, but we can assign it to 4 locations. Okay, so this is an unbalanced model. So the estimated cost in dollars per hour to material handling involving each of the machines is given in the following table. Location 2 is not considered suitable for machine 2, so no cost is given. So we can't put machine 2 at location 2. Okay? For whatever reason, it's a power supply and it's near water, something like that, whatever it may be. Okay, to formulate this problem as an assignment problem, we must introduce what's called a dummy machine to the extra location. Also, an extremely large cost of M should be attached to the assignment of machine 2 at location 2 to prevent this assignment in the optimal solution. So remember when I talked about the big M? We're going to use it here. So what I'm going to do is to prevent machine 2 from going to location 2, I put a big value in, okay? 2,000, something like that. This dummy machine which is a machine that doesn't exist. It can be at any location. So I'm going to put cost of 0 here. All right. The reason why we do this is to make it balanced. This matrix has to be an n by n matrix. Okay. All right. So let's go in and look at this. All right. So let's go in and take a look. Okay. So my total cost is simply going to be the sum product, my decision variables, times the cost over here. These sums, all these, I'll show you, they're going to be equal to 1. So I want to minimize my objective function by changing these decision variables. This sum has to be equal to 1, this sum has to be equal to 1. I don't even need the binary constraint. And I hit solve, and maybe I do need the binary constraint. Why did that happen? Oh, non-negative. That's a case where you need non-negativity. And the reason why is because sometimes you can actually get a, well, in this particular case we want to minimize. So if you allow negative numbers, it's real easy to minimize. Just plug in negative a trillion and you're going to minimize. Okay? Also, this is a simplex linear. So there we go. So here's what it says. It says machine 1 goes to location 4, machine 2 goes to location 3, machine 3 goes to location 1, and machine 4, which doesn't exist, goes to location 2. So we only have machines at location 1, 3, and 4, and that total cost will be minimized at 29.
You had to create a dummy machine because you had more locations than machines.
We had more machines than more locations than machines. Yeah. Exactly. So you do this all the time. You have dummy variables. Dummy sources or dummy sinks is what they're called. Okay? All right? And you may look at it and say, well, why do you have to have that dummy machine, or that dummy machine? The reason why is because of this. Is because not all of these then would be equal to 1. So you couldn't force them to be equal to 1. You see what I'm saying? 3 of them would be equal to 1 and 1 of them wouldn't, but how would you know? Okay? There may be a way to go in and do it. You may be able to take the sum of the sum, force that to be equal to 3, force everything to be binary integer. But at that point, what happens is you lose the special characteristics of this problem. If I force them to be binary integer, okay, what would probably happen, it's going to start using a branch and bound approach, which for a problem like this, you'd be like, well, so what? I've got the answer, who cares? But if it was a really, really large assignment problem, you would see very quickly that that branch and bound approach is far inferior to just using a linear programming approach. So the sacrifice you make in complexity of adding dummy machines, dummy sources, dummy sinks is far more than made up for by the efficiency of the simplex algorithm versus the efficiency of the branch and bound algorithm, right? So that's fundamentally why we would do that. Okay, so let's see. Just shows you how to go in and do it. Yeah. Okay, so any questions on this? Well, if not, then you guys get the exam to me and go ahead and start on the project, and it will be due next Tuesday, okay? And it's posted on the web under the exam folder, okay? What?
Did you get ours? Under the door.
Yeah, I did.